together. The first thing that I'll ask is, what happened?
Right, we've gotten this question before.
Say it.
I feel like what we prepared for was not on the test. At least personally.
So I'm not gonna disagree with you. I want to understand. I felt that we were all prepared. Okay, so determine the values for B such that that plane is parallel to a line. So if I have a plane, if I have a piece of paper, and I want a line that's parallel to it, the first thing that I saw was everyone trying to find a vector that was parallel to the normal vector. But don't forget, that's the normal vector. That is a perpendicular vector. So if you want your line to be parallel to the plane, what needs to be true about your normal vector and the direction vector? They need to be perpendicular. If two vectors are perpendicular, then the dot product equals 0. So you would have found the dot product of your direction vector and your normal vector, set it equal to 0, and solve for B. Two, I don't think there were any issues across the board here. I think we generally had the equation of a sphere equals r squared. You can plug in the other point to get a value for r squared. The only thing I think I saw was accidentally writing equals square root of 42 or something like that. I think two is pretty good. So given the surface, sketch the level curves. You can plug in z equals -3 and then sketch that two-dimensional equation. If you have no idea what that looks like, that's fine. We have Desmos in front of us. And you just want to be able to sketch the level surfaces. Only minor things like, maybe we mislabeled some z's, but generally 3 was pretty good.
So in that we would have had to use Desmos 2D to find.
Didn't have to, but yes. So coming over here, I have x squared minus 2y squared. Plus z squared equals 1. And I'm going to sketch this for z equals -3, graph that. -2, graph that.
Oh shoot. Okay.
Or you could have said this is like L, and then just graphed all of them at once. This way it gives you the entire picture, but you lose sight of which level curve is which. So doing it individually would have just helped you see, like, okay, well, that's the first equation. I'm going to label that as equals -3. Or write the equation of a line that passes through the point and is perpendicular to the YZ plane. So the first thing I don't think anyone got wrong. The YZ plane, if I want to be perpendicular to the YZ plane, I'm looking at x equals 0. Okay? Well, don't forget that can be written as 1x, and no y's, and no z's. So my normal vector is 1, 0, 0. So now I have a point, I have a direction vector, you just drop it into your vector component. Did not matter, by the way, if you wrote it in this form or in this form, those are both technically vector component form. So again, I think everyone had x equals 0 written. The only thing we missed was being able to think of that as a direction vector. All right, let A equal this, B equal that. Determine a unit vector perpendicular to two vectors. How do you find a vector perpendicular to two vectors? That's the cross product. This is essentially just showing me, or saying, show me you know how to do a cross product. and then maybe dress it up by then just finding a unit vector. It seemed like everyone was totally cool on the unit vector part, but we missed that a cross product gives you a perpendicular vector. Questions on any of the free response? First one, what is the distance between the origin and the point where the xy plane intersects with the line? So find a point of intersection, and then just find the distance to the origin. The xy plane means z equals 0. So we can set our z equation equal to 0, find a t value, plug it back in. That is now only the point. You can find the distance from the origin, 0, 0, 0, to the point 680. Two was pretty good across the board. I don't think we had any issues there. Which of the following vectors is perpendicular to both A and B? So in my solutions, I did this kind of silly. I found a cross product and then just looked through the answer choices and found a scalar multiple of my answer. But what's the best way to do this? Someone's solution had the even better way of answering this problem.
I found it and then multiply the vector by
You just
-1.
find the dot product. And if the dot product of the two vectors is 0, you can just go through the answer choices and go dot product, dot product, dot product. Oh, cool. This is the first one that gives me a dot product being 0 for both of them. You don't even need a cross product here. That's one of the cool things about multiple choices.
Okay, that it is.
The path that you take isn't necessarily going to be the same.
Okay.
Okay, this one was hard. Everyone was given 5 points back. I feel like maybe we didn't emphasize this idea enough. So the 5 points difference between what's on the test and what's on Blackboard. Write the equation that represents a distinct plane, meaning it can't be the same plane. So I think we're all on the same page. We said, okay, well here the normal vectors are parallel, so a parallel plane, check. Here we said, okay, normal vectors are parallel, check. But if you multiply everything by -1, you get the same plane. It says a distinct plane, basically a different plane. And then rearranging this, you find out that this is a scalar multiple. So it should have been 2 and 3. Again, I feel like maybe this wasn't emphasized enough, so I threw that problem out. Everyone got 5 points back. 5 kind of upset me though. Describe the shape of the intersection of this surface and the plane x equals 2. You just plug in x equals 2, you get an equation, and you have a reference sheet in front of you. You just say, oh, well, what does this look like? This should have been the easiest one to spot, because if one of the terms isn't being squared, that's a parabola. That's just like algebra 2 stuff. Something squared, algebra 2, parabola. 6 was pretty good across the board. If we made a mistake, what do you think the biggest mistake would have been here?
Forgetting to take arc cosine.
That's exactly it, yeah. We had our calculator in the wrong mode.
Oh.
So if we had A, you had almost the full answer. You just didn't make sure that your calculator was in degrees. It should have been a signal when you get an angle of 1. Okay, maybe we need to check something. Select the equation of the line below that is parallel. I don't think there were any issues here. We combined a vector that is a scalar multiple of our direction vector. See which one matches. I think everyone had the same technique of just make the x coordinate or x component be 1 and just see which one matches that. This is another one that we should not have been missing this one. So it says the statement in R3. in 3 dimensions. Y equals 2x plus 3 is not a line. That's a plane. X equals 3 is a plane. I think we all recognize that one. But x squared plus y squared equals 4. It's a cylinder in R3. I agree in R2 it's a circle. In R3 it's a cylinder with radius 2.
Okay.
So 9, we recognize this is just a half cone. So don't forget the full cone on our reference sheet is kind of this symmetric image here. So if it's only a half cone, I need to restrict it and only have positive z coordinates. So I'm looking at these. I look at my reference sheet and this says, well, hang on, it says x squared plus y squared minus z squared. Oh, well, if we just multiply everything by -1, that is the same equation. 10, the 2 vectors are given that are perpendicular to each other. It needs to be true that the dot product is 0. If the cross product is 0, that means that the 2 vectors are parallel, so that's false. And this says if you have 2 vectors that are already perpendicular, does there exist a third vector that is perpendicular to both A and B? That is true. If I give you 2 vectors, you want to do your right-hand rule, and you just make your 2 vectors perpendicular, there does exist a third vector perpendicular to both of them. And the best example is I hat, J hat, K hat. Those are 3 vectors that are all perpendicular.
Okay.
So after seeing the exam and talking about it, what are we thinking?
I felt I should have did a lot better.
But what specifically?
I don't know. I think can we marinate over that over the weekend and go over the test a little bit and get back to you on Monday? Because I know you want us to do better.
Yeah, I want to make sure that we're all on the same wavelength as what is expected of us, and maybe some reflection as to time that went into it and stuff like that. All right, let's actually keep Desmos out. If you guys give me 2 seconds, I'm gonna run downstairs, make some copies. I do have a course topics list for the second unit.
You know what? In saying that you felt that what we did in class and the tests didn't prepare us, see, but that's how all his tests are terribly hard. So what he does, he gets you to like I don't know. He wants you to build a bridge. He gives you all the pieces to build a bridge, and then once he gives you the test, he expects you to be able to think through the test and build that bridge and get to the other side to solve the equation. But my thing is, I can never build a bridge. Because he gives us all the information, but you have to be able to think through and be like, okay, how do I solve this problem? And
I think it's like a critical thinking type thing.
yeah.
I ended up doing fine on it. Yeah. Because I mainly just went through the 3 practice exams he gave us, and I forgot to make one sheet of them, so I was just kind of going in blind, but I ended up doing fine.
Yeah, I did horrible. I thought it was going to curve it. I was like, where's the curve?
Yeah.
But the lowest test drops, so we just have to.
It's crazy that this is the first one.
Yeah. Oh, believe me, it gets a lot harder. It really does get a
We
lot
haven't got to
harder.
the calculus stuff.
Yeah,
No,
it gets.
it's just, like, I
It-
think the thing that like fucked me up, was definitely like just the way that he like asks the questions.
Yeah,
Cause I think like when we're in class, like we don't really get practice with the way that the questions are asked.
yeah,
We just like, oh, okay, we know that we're gonna, cause what we just learned today was dot product, so we're gonna be using dot product in all
Yeah.
of this.
yeah.
So I think that's probably what kind of got most of us, cause I think like these concepts were not hard, like they're pretty simple.
Yeah.
But it's the actual like,
It's that like you said, that critical thinking to where you have to say,
more
okay,
than just like, okay, well, I know we're doing dot product today.
yeah. Because then you got a whole bag of tricks, but you like, okay, you get to the problem, like, okay, what trick do I pull out?
Yeah.
Like, you should
Yeah.
know what you're working on, and then it ends up making it just easier. But then you're throwing everything together.
Mm.
It's just we have like hard homework, you know?
Ah, that would help.
Like,
Okay, there we go.
Homework.
Hard
is
homework.
So helpful.
I'm sorry?
It's like-
To help with
Really
the critical
have, like,
thinking.
Homework.
Or like
type
hard
thing.
practice problems, because all the practice problems were so light, like.
Easy. Really, basically
I also
easy.
think like they were also asked in like a different way, like on the practice exams.
Yeah, exactly. And if he gave us homework that was more tailored toward the questions you're gonna ask during the test. Okay, if you can figure out the homework, then you're gonna get a good grade on the test. So yeah, so I think that would definitely help out a lot. Homework. We brainstormed a bit.
Okay.
We're thinking homework more tailored to how the test questions are put together. Because we understand that it's the critical thinking part that once we get the test and we have to be able to figure out, okay, what to use and how to solve it. But we're thinking like hopefully some homework questions.
I think what got us the most was just like, or at least for me personally, and from what I'm kind of hearing, is that like, it's the way that they're asked. Because like normally whenever we get into class, it's like, okay, we know that we're doing cross product today. So pretty much all the questions that we're going to be doing are cross product. But then each cross product question or dot
You're
product
knowing
is
you're
kind of-
looking to use the cross products.
Yeah, asked in a different way. So then when we get the test and it's like, okay, I have all of the materials in order to build, you know, whatever this is, but I don't know, like I don't have the plans for it.
Exactly. The blueprint. Yeah.
So maybe I'll try something different in this unit where maybe like every couple lessons, I'll make some like, if we had an exam today, this is what a popcorn shuffle of everything we've learned so far for unit 2 would look like.
Yeah, that might be okay. That'll work.
So, looking over, kind of glancing through Unit 2, so the theme of Unit 1 was all about, 3D space, geometry, how does 3 dimensions work, how do vectors work in 3D. The theme for Unit 2 is finally starting in calculus. So in the beginning, we're going to talk more about vectors and different kinds of coordinates, but it's really going to start when we talk about partial derivatives.
Yeah.
And we're going to revisit a lot of the topics from Calc 1. So believe it or not, your understanding in Calc 3 is directly proportional to your understanding of Calc 1. So we're going to review a lot of Calc 1 stuff. But if you get the Calc 1 stuff, we're just extending it to 3D. So the biggest thing is, if we're a little rusty, it's been a while, I'll post some Khan Academy videos as it gets closer to talk about just derivatives in general. And then just a reminder, the final exam has the ability to replace your lowest test score. So I don't want to think everything's set in stone. By the time the exam rolls around, we get it, we figured it out, then we're gonna get better.
Yes.
Okay, so a vector value function. So we've actually seen this before when we were looking at equations of lines. So these vector value functions are functions that input a t, so you input a number, but the output is a vector. So if you want to consider like v of 0, you get x of 0, y of 0, z of 0, those are all numbers. Your output of this function is a vector. So we were looking at this with lines, and we were just understanding, okay, parametric equations, vector component forms. Now we get to actually do some math with them. So it turns out that if you want the derivative of this vector value function, then you guys are gonna love this. You just take the derivative of each of the components. And again, if you want the second derivative, you just take the derivative of the derivative. So just think back to Calc 1, and all my derivative rules, those are still coming back to haunt us, all the gateway stuff. The derivative of sine is cosine. The derivative of e to the t is e to the t. Derivative of 2t plus 3 is just 2t. So if I want the second derivative, I get negative sine t, e to the t, so let's go ahead and look at visually, what would a derivative give me if we're taking the derivative of a vector value function? So I'm going to do my vector value function sine t, cosine t, comma t. So this is a helix. And I'm going to scrunch this down a little bit. So I have my space curve. If you want to think of this as a vector value function, then all we're doing is simply just thinking about the vector starting from the origin and landing on whatever we're outputting. So for any input t that you give me, this is just outputting a vector. And if you want to think about tracing out all of the different vectors as just points, then you get your space curve. So if you're thinking, well, this feels just like what we did with parametric equations, it is, The only thing different is if you treat that coordinate like a vector, then you can do math with it. You can find derivatives, you can add them together. So it's just a conceptual leap, not really a computational leap. So my derivative vector is cosine A negative sine A, comma 1. And now thinking about this alone as a vector doesn't really help me until you add it to some point on the curve. So once I have my point on the curve, I now want to have a vector starting at the point, and I will name these things to make life easier. There we go. So this is our tangent vector. So it contains the point, and just like we kind of expect with our derivatives, it's going to point in the direction that this, if you want to think of it as a particle, it's pointing in the direction that this particle is traveling. So looking at the vector alone by itself, say I give you some, general A prime of 3, and you get the vector 2, negative 1, 0. This is saying, at this moment in time, your x component is increasing because your derivative is positive. So at that moment in time, you're increasing in the positive x direction, decreasing in the decreasing in the y direction, and your z coordinate is not changing. So here, this is just tracing out a tangent vector. You can see it's kind of pointing left and right, and also if I tilt in the z-axis, notice this points just slightly up because I have t for my z component. The derivative is 1. So my z coordinate is always increasing, is what that's suggesting. So take 2 seconds, try to generalize this. So completely start over and start off with f of t, g of t, h of t. And we're just going to save a quick Desmos sheet. That gives you the tangent vector. So call them f, g, and h. I just put in sine, cosine, t as a quick example. So first, I want a point. Well, I want my space curve f of t, g of t, h of t. So to get the point, I'll call that P. That is f of A, g of A, h of A. Now we do like a contrasting color like orange, so you can see that. To get the tangent vector, just call it t. Your tangent vector is f prime of A, and Desmos just knows how to compute that. G prime of A, H prime of A. And we can just turn off that point. We don't want to see that vector by itself, so just turn it off. And now, to get the tangent vector, you want the vector starting at point P and ending at P plus the tangent vector. Boom, you got a tangent vector. So now, play around with this. Now you can go up to the very top and change F, G, and H. Put a 2 in front of this. And now it's still always going to draw your tangent vector. You can do cosine of 3t. You get this interesting curve. And you can see as time progresses kind of where is this pointing in the direction. If I change h of t to say 5, what should I notice about my tangent vector? If the z component is a constant, what should I see in the tangent vector? If I change my z coordinate to just 5, it means that z is never increasing or decreasing. So we get something that just lives in the plane z equals 5. So now moving around with this tangent vector, the tangent vector is always parallel to the xy plane. Because the z coordinate is never increasing or decreasing, its derivative is 0. Once you've got those, go ahead and just save it. Now you have a tangent vector sheet in Desmos. While you guys work on that, I'm going to walk around. G prime of A, H prime of A. Nice, that looks tangent. And we just don't need to see this blue dot, so you can just, don't delete it, just turn it off. Nice. And now slide A around, and you can see that you get a tangent vector at all those points. Oh, I see. Just spin it a bit. I see. Yeah.
catch that fly one of these days. I'm gonna catch him.
So in Calc 1 and Calc 2, when we start doing all the, velocity, acceleration, all that normal stuff, application to physics, it's always one-dimensional. So that the problems are always like, oh, a particle is moving along the x-axis. Now that we have three-dimensional space, it's usually some sort of fly or something moving around in the room. And something will always be in the prompt that describes what it means to be the origin. So I could make the origin a corner of the room, and now the room is maybe just the first octant in 3 dimensions. Or you could define the center of the room to be the origin, and then you have positions going from the center. So something in the prompt will always just describe, like, what does the origin mean? So the position of a fly in a room is given as s of t. Now I have a vector value function. And let's just go through all the different possibilities of things that we're going to be asked to do with these vector value functions. So find the velocity vector at time t. We remember if you have position, and the derivative of position is velocity. So now your velocity vector is just going to be the derivative. Just like we saw a second ago, we can just take derivatives of each of our components. So not only being able to compute the vectors, but also make sense of them in some sort of context. So this says find the position of the bug at time t equals 1. So that's going to be my position function. And the position is just s of 1.
Why are we keeping the plus 1 there?
We should know that. It's just negative 16. Sorry, I want the position. Plug this into the position function. So although, yes, this does give you a vector, and you can think of that geometrically as, the kind of arrow idea, this is still saying that this bug has a coordinate, has a position of 5e negative 2. So 5, 2.7-ish, comma, negative 2. Again, we can just treat them as vectors so we can do math with them. We can take derivatives, add it together, things like that. So we have our velocity vector, but let's make sense of what that velocity vector would mean at given standards. So this says, is the particle moving towards or away from the floor at t equals 1? So this is not asking where is the particle at t equals 1, but where is the particle traveling? And the direction of travel comes from your velocity vector or your tangent vector. So my velocity vector, which I'm just rewriting it over here so we can see it, is 2 e to the t negative 60. So now let's think about v of 1. So just making sense of this again, you can think of s of 1 as being the coordinate or the point, the position, the location. This velocity vector is saying at time t equals 1, and don't forget derivatives, I'm just looking at increasing, decreasing, positive or negative. You are increasing in the x direction, increasing in the y direction, decreasing in the z direction. So if this represents the position of a bug, the question is asking, are we moving towards or away from the floor? What does my velocity vector suggest?
Towards the floor.
You're moving towards the floor. Your z coordinate is decreasing. So we're going to say moving towards the floor. As the derivative at 1, z prime of 1 is negative. So a lot of those conceptual Calc 1 ideas are still there. This is saying compute the normal tangent vector at time t equals 1. So tangent vector, velocity vector, same idea. Or, excuse me, sorry, not normal tangent, unit tangent. If I want the unit tangent vector, then I want my tangent vector, but I'm just going to normalize it or shrink it down to where it has a length of 1. So peeking back over here, this was my tangent vector at time 1, t equals 1. So now let's just find the unit vector. That's where we find the magnitude. And then we're going to divide each of the components by the magnitude. So a lot of those vector computations, ideas don't go away from example one. You're still gonna be asked to find unit vectors, take the magnitude, divide each of the components by. Questions so far? So if I have my tangent vector, then this points in the direction of travel, and you can extend that vector short or as long as you want, and you can also extend it in the negative direction by scaling it by a negative number. So if this just gives you a direction vector and you have a point, you can make a tangent line at that point. So it's going to be the same idea, and it might be easier to do it by hand, but it's still going to be the point plus t times my direction vector. And you can see you can still make a tangent line just like you did in Calc 1. One more thing we gotta do. We'll just practice problems. If you want the definite integral of a vector value function, then just like derivatives, we're gonna like this one, you can just take the definite integral of each of your components. Okay. So let's see an example of that. So I want to compute a definite integral of a vector value function. That is just going to be the definite integral from 0 to 4, my x component. Excuse me, guys. Definite integral of my y component. thinking back to calc 1, calc 2, the definite integral from 0 to 4 of 3, you're just doing three definite integrals. Antiderivative of 3 is 3t. And then I want to evaluate from 0 to 4. Antiderivative of 2t is t squared, 0 to 4. Antiderivative of e to the t is e to the t, 0 to 4. Fundamental theorem of calculus says plug in the top bound. Minus plug in the bottom. Three times 4 is 12, minus 0. 4 squared is 16, minus 0. Just be careful with the last component. What's my z component?
Z component is going to be plus, right?
E to the 4th minus what? Minus 1.
Plus 1.
So the other thing that we did with integrals back in calc 1 or calc 2, so the first one is compute definite integrals, maybe. The second idea was you can find antiderivatives of functions. So if I give you a derivative, v prime, then we can find v of t. Just don't forget what happens there. You take the antiderivative, you get a plus c. Then you have to have some sort of initial condition to help you find what the c was. So you're going to be given an initial condition for the vector v. So v of t I've got the antiderivative of 3, antiderivative of 1 over t, antiderivative of 60. The antiderivative of 3 is 3t plus c. Antiderivative of 1 over t is ln absolute value t plus c. Well, hang on, we need to pause there for a second. If you write plus c and plus c, it kind of suggests to the reader that these would be the same value. But they're not necessarily the same, so we can call it C1, C2. If you want to say it's plus C plus D, or plus A plus B plus C, some way of showing that these are not necessarily the same constant. That would be 6t squared over 2, so 3t squared, plus C3. Please ask questions so far on just the antiderivative. So now I'm given an initial condition. This is saying when you plug in t for 1, or 1 for t rather, you should get 4. So go over to your x component, plug in 1 for t, and you know that should be equal to 4. So in my scratch word, 3 times 1 plus c, and I'm going to write it like this. X of 1 is 4. When you plug in 1 into your x component, you should get 4. So that was just helping me find C1. I'll give you guys a 30-second head start to find C2, find C3, and then plug them back in. To write your V of T equation. So I found C2, I found C3. Don't forget, that last thing we need to do is now just go ahead and plug them back in. So this is my original vector value function. It needs to be true that when I plug 1 in for t, I need to get the vector 4, -2, 5. If I plug in 1, that's 4, check. If I plug in 1, 1 is 0. -2 is -2, check. And 3 times 1 squared plus 2 is 5, so that looks good. It also needs to be true that when you take the derivative of this, you should get v prime. Derivative of 3t plus 1 is 3. Derivative of ln of t, even if it's an absolute value, is 1 over t. The derivative of 3t squared plus 2 is 6t. So we know we do.
Okay.
do you get the page on this?
Um,
Can you like upload it from? Oh, no, it's you taking notes.
yeah,
Gotcha.
But I can make some PDF, put it on like or something like that. That's all.
So I do want to spend more time looking at this stuff. So maybe on your topics list, just add another bullet beneath vector value functions and call it vector value functions part two. So again, when we come in on Monday, we're still gonna hang out in this topic here. Just shake off all the rust when we talk to, take the anti-derivatives, throw some applications in there with velocity acceleration, things like that. Alright, what is something that I can do to make sure that we're still on the same page moving forward?
It's like harder practice probably, first, like, I think the best lesson we've had like the possible but like easy.
Would we benefit from a retake?
Oh.
Yeah, I definitely.
Now, I'll say this, it has been my experience that if I do a retake, scores improve by like 2 points.
2 points.
Is it
It's not the
how the test was written, or do we just understand like, oh yeah, I wasn't prepared, like I should have.
I studied for like hours.
So, but this is what I don't wanna run into, I don't wanna run into writing a new test and then we're running into the same issue. Cause, did we not feel like it was close to the practice tests?
I feel like it was pretty close.
Of course you did. You got a good score. Why wouldn't you?
From personal experience.
So, look out on Blackboard for, I'll have some sort of, it'll be outside of class on a blah 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 day, you can swing by and take it again. But before that, I would only ask that, maybe let's find a time to talk one-on-one, just to talk about your exam. If it's like, oh, I know what mistakes I made, I just don't want a chance to do it again.
No.
Cool. Alright,
Thank
I will
you.
see everyone next week.
Hey, roger that.